Hello and welcome to today's webinar on strategies for mycotoxin testing with perspectives from screening in the field to confirmatory analysis in the lab. My name is Ken Rosnack and I'll be your host and moderator. Thank you for joining us in our first part of a four-part webinar series, Stay Ahead in Food and Water Testing. For today's agenda, we have three great speakers who will be sharing their perspectives on the importance of mycotoxin testing and the range of options available to protect crops and consumers using upstream, field tests, and laboratory-based methods with HPLC and LC-MSMS. They will provide overviews and best practice experience for the range of solutions available for mycotoxin detection and measurement. We will conclude with our Q&A session once we've heard from all the speakers. You may submit your questions along the way, but please make sure you indicate to whom the question goes, either Patricia, Simon, or Nicola. Before we get started with the presentations, however, I want to cover some basic options within the console. Please post any questions you have at any stage into the Q&A chat box. I'd also like to draw your attention to the feedback box on the right. If you would like to learn more about the solutions described here today, be sure to let us know in that box. All of our speakers' biographies are available to read, along with some downloadable content in the resource list, and this includes slides from today's presentation. Now, if you're missing any of the panes shown on my screen here, simply click the appropriate icon in the control bar along the bottom of your screen to launch that particular widget. And with that, I thank you all again for joining us, and I'll hand over to Simon, who will give us a short introduction to today's topic of mycotoxins.
Good morning, good afternoon, good evening. Welcome to the start of today's webinar on an introduction to strategies for mycotoxin testing from the perspective of the growers to laboratory analysts. I'm going to start with an introduction to set the scene. So in this introduction, I'm going to cover the occurrence of mycotoxins, some information on regulations, a little bit to introduce the concept of emerging and modified mycotoxins, and then a very short piece on analytical considerations. Mycotoxins are toxic compounds that are naturally produced by different types of fungi. They enter the food chain as a result of infection of crops, including nuts, fresh and dried fruits, vegetables, cereals, things like corn, maize, rice, wheat, coffee beans, and cocoa. Because they are stable compounds, mycotoxins in their metabolites are also detected in finished food products, for example, aflatoxins in milk. Contamination can occur pre-harvest when the crop plant is growing or post-harvest during processing, packaging, distribution and storage. Mycotoxins are well established to have health impacts both in humans and animals. Depending on the quantities consumed, mycotoxins and the metabolites are associated with severe acute poisoning, including death, and chronic adverse health effects. Human exposure to mycotoxins can happen by eating contaminated foods, but also from animals that are fed with contaminated feed. Most mycotoxins are chemically and thermally stable during food processing, including cooking, boiling, baking, frying, roasting, and pasteurization. The economic impacts of mycotoxins to human society can be thought of in two ways. The human health losses from adverse effects associated with mycotoxin consumption, but also the direct market costs associated with lost trade or reduced revenues due to contaminated food or feed. Losses related to markets occur within systems in which mycotoxins are being monitored in the food and feed supply. Food that has mycotoxin levels above a particular maximum allowed level is either rejected outright for sale or sold at a lower price for a different use. Such transactions can take place at local levels or at levels of trade among countries. Sometimes this can result in heavy economic losses for food producers, but the benefit of such monitoring systems is a lower risk of mycotoxins in the food supply. The FAO estimated 25% of crops are contaminated with mycotoxins, but this does not tell the whole story. Iscola and his co-workers tried to determine the true picture by looking at the occurrence at levels below regulated limits, and we can see that they concluded that the global mycotoxin prevalence in food crops is much higher, up to 60 to 80%. There are hundreds of mycotoxins known to exist in crops, but this slide shows a list of the compounds that are considered to have the greatest importance from a food safety and regulatory viewpoint. In many cases, analytical methods will be restricted to covering just these compounds. The annual Biomin surveys is a very useful source of information on mycotoxin occurrence. I can recommend folk to take a look at the Biomin website and their work on tracking occurrence of mycotoxins across the world. Here we can see results from the 2020 survey, which give us the key mycotoxins that are found, and also the fact that 6.5 out of 10 samples had at least one mycotoxin above the threshold level. The Rapid Alert System for Food and Feed, RASIF, is a tool designed to swiftly exchange information between national authorities within the European Union on health risks related to food and feed. Mycotoxins are consistently in the top 10 hazards reported through this system. The graph on the right shows the percentage of RASIF notifications for mycotoxins in food products according to the country of origin during 2010 to 2019. The most notified country of origin is given in red, which was Turkey, with 104 notifications. Aflatoxins were the most frequently reported mycotoxins. Climate change is reported to have significant effects on the security of stable commodities. Mycotoxin occurrence in cereal grains is both directly and indirectly related to local weather and to climate change. For example, the impact of elevated CO2 levels, increase in temperature and or rainfall, and drought stress all impact on mycotoxin production. In 2013, Romania, Serbia, and Croatia all reported significant aflatoxin M1 contamination in milk, and this was related to the severe droughts in Serbia the year before, which resulted in a considerable amount of the maize crop being contaminated with aflatoxins. This maize was used to feed dairy cattle, and which led to the very high levels of aflatoxin M1 in milk. Legislation is one way to protect the consumer from the harmful effects of mycotoxins whilst continuing to facilitate trade. Different factors play a role in the decision-making process of setting limits for mycotoxins. These include scientific factors, for example, the availability of toxicology data and occurrence data, detailed knowledge about the possibilities for sampling analysis, and socio-economic issues. Regulatory limits for mycotoxins are very low in concentration due to the severe toxicity associated with mycotoxins. They typically include values that are specified for various foods and feed commodities, and these are either maximum allowed levels or guideline/indicative values. In addition, regulations often include information on sampling plans and analytical method performance criteria that need to be used for official control of mycotoxins. The Codex Alimentarius Commission has established maximum levels for mycotoxins in food and feed at the global level. These are voluntarily applied by the Codex member countries. Codex levels are considered as neutral and generally accepted as global standards. They are used to resolve trade disputes, and national mycotoxin legislation in many countries are based upon them. In addition to these Codex standards, many countries have their own national mycotoxin legislation. In the EU, for example, maximum levels have been set in various foodstuffs for aflatoxins, deoxynivalenol, ziranolone, ochratoxin A, fumonisin, and patchoulin. Current regulations very rarely consider the exposure to multiple mycotoxins from different groups, and they are either based on a risk assessment of a single compound or their sum. This is a list of global limits for aflatoxins. We can see the variation in the limits between different countries. We can also see that some countries have established levels just for aflatoxin B1, whereas others look at a total of aflatoxins. We can see some of the levels are established just for specific crops, for generic crop descriptions, such as in Japan, or food crops, and for example in the European Union, different levels established for different types of commodity. Some countries operate strict import rules with respect to food and feed safety. Goods being imported, for example, into the European Union are sampled and checked for mycotoxins. These plans are based upon the frequency of detection of mycotoxin in imported goods in previous years. For example, currently 50% of consignments of pistachios from Turkey are checked for aflatoxins. The term emerging mycotoxins is used to describe a growing group of chemically diverse compounds for which far less information is available. These are not really emerging as such, as many of these compounds have been known for years. However, testing for such toxins has significantly increased over the past decade, in part driven by the development of multi-toxin methods based upon LC-MS. Risk assessment studies are underway, and legislation for some of these toxins is likely in the future. For example, maximum levels of ergoalkaloids have been proposed in certain key foods and relevant commodities in Europe. Another group of compounds of growing interest are the modified mycotoxins. After infection of plants, mycotoxins are modified by enzymes and often conjugated to more polar substances like sugars. These often less toxic metabolites are stored in the vacuole in soluble form or bound to macromolecules. As these substances are not usually detected during routine analysis, nor any maximum limits are enforced, they were initially called masked mycotoxins. Whilst having low intrinsic toxicity, masked mycotoxins might be reactivated during mammalian metabolism. In particular, the polar group might be cleaved off, liberating the native mycotoxin, increasing the risk to human and animal health. For example, when we look at the mycotoxin DON, we can also have metabolites, the 3 and 15 acetyl DON, and also a glucoside, DON3 glucoside. The co-occurrence of different mycotoxins in a single sample is of growing concern. Here we can see some results from the BioMin survey, where 87% of the 1,000 samples analyzed by BioMin using their LC-MS methodology contain 10 or more compounds. This is driving the interest in multi-toxin approaches to investigate the true pattern of mycotoxin contamination. There is a need to guarantee that controls are in place to ensure that exposure from food is as low as reasonably achievable. This includes ensuring that good practice is undertaken during growing, harvesting and storage of foods, establishing maximum levels where necessary, evaluating the risk by routine testing using in-field and in-laboratory detection methods, and discarding any contaminated batches, and any official monitoring programs. Contamination with mycotoxins can occur at various stages of production of food and feed, so the timing of the analysis is vitally important. A large number of tests needs to be carried out to make sure results are statistically valid, which means that each test should be performed as quickly as possible. The question then of what to analyze, when to analyze it, and where to do the test is important, and often determines the analytical approach to be used. A variety of testing solutions exist. We have lab-based tests, some of which are multi-toxin methodologies. These are maybe considered expensive, complicated, and time-consuming, but they provide a comprehensive view of the type and level of contamination. We also have easy-to-use rapid tests, which can be used at the point of production and at stages of distribution and food production. For example, if we picture a line of trucks containing produce arriving at a storage facility, each requiring testing before acceptance into the facility, how are you going to do this effectively? And that brings us to the end of this introduction. I would like to hand over now to Patricia.
Thank you, Simon. That was a very nice introduction to the topic of mycotoxins. I especially appreciated what you presented on recent research and surveys on the occurrence of mycotoxins. It's very important for us to have a strong understanding of which mycotoxins are most prevalent, but also whether we're dealing with a single mycotoxin contamination or could there possibly be more than one mycotoxin affecting a raw material or a finished product? My name is Patricia Jackson. I'm the Market Development Manager for VICAM. My background is in the biological sciences with a degree from Iowa State University, and this month marks my 23rd year with VICAM. Through those years, I've had the pleasure of working with many different types of food manufacturers, as well as their raw material suppliers. Today, my presentation will focus on how mycotoxins are impacting food manufacturers, the need for preventive monitoring, and how lateral flow strip tests in particular can play a role in preventative monitoring upstream and in the processing of foods. When we think about the types of products that might introduce mycotoxins into the food processing environment, there are some raw materials that are rather obvious and have been discussed widely, such as cereal grains, tree nuts, peanuts, also known as ground nuts in some regions. What might not be as obvious is some ingredients used to a lesser degree but may still carry a significant risk for mycotoxins, and that could include spices, dried fruits, herbs and botanicals, even cocoa and coffee. Once we've identified which raw materials are at risk for mycotoxins, how do we know which mycotoxins need to be tested on a regular basis? We can actually start to look at this question without doing any analytical testing at all. And one way we do that is by asking, where is the commodity grown? What are the climate conditions during cultivation? What about during harvest? How is that product stored and for how long prior to being delivered to the food processing facility? How is it being transported to the facility? How much time is it spending on a ship, in a truck, or on a rail car? And what are the temperatures and the relative humidity during all of those processes? Are good agricultural practices being followed? Once we know the answers to that, it will really help us to focus in on which molds might thrive in those conditions, and therefore which mycotoxins might be present. One thing to keep in mind, you can have mold growth, even a mycotoxin-producing mold, growing on your product actively, and absolutely no mycotoxin production. You can also have a commodity arrive at the facility that looks pristine and doesn't have any visible mold on it, but it contains high levels of mycotoxins. It's just the nature of the molds either being internal to the product, or it could have been brushed away during handling and movement. So we can't count on visual indicators to tell us whether a raw material is contaminated with mycotoxins. So most of the mycotoxins that you're going to bring into the processing environment tend to come through the front gate in those raw materials. However, there are cases where mycotoxin production can get started or begin to occur in storage and processing. Processing in particular where there is a higher temperature and a lot of moisture, steeping, for example. Barley malting is another good example. In the case of barley malting, you're going to be spending a significant amount of time in that warm water condition, giving just the perfect opportunity, if that mold is present, to start producing toxin or continue producing it if it already was there. That's why the brewing industry as a whole is very cautious and careful to accept the highest quality barley that they can on intake. And finally, finished food products, and this is what we all hope doesn't happen because there aren't a lot of options. The mycotoxins are very heat stable, very difficult to handle them once they are in a finished food or feed product. It usually takes enzymatic activity or heavy chemical processing in order to clean up mycotoxin contamination, which often results in food products being destroyed or rejected at the final destination. So what's driving the need for rapid mycotoxin testing, in particular outside of the laboratory? In addition to the science showing us repeatedly the risks to human and animal health, and also what we know about how mycotoxins enter into the food processing environment, We also have the last decade of intense regulatory activity, whether that is additional regulatory limits on specific mycotoxins, and also the food safety initiatives that are being implemented and enforced around the world. There's a growth in the certification and audit sector, and the Global Mycotoxin Surveys help inform all of these programs and help us to know which mycotoxins are important and which are urgently needing oversight and management. And of course, brand protection, which always has an important seat at the discussion table around food quality and safety. We know from the science that long-term exposure to low levels of mycotoxins can cause a wide range of disease in humans and animals, cancer being the biggest risk, especially with aflatoxins. It can also cause immune suppression, reproductive problems, kidney and liver disease, as well as a host of other issues. But what we all see, what appears in the media, is usually the acute poisoning that can happen with unusually high levels of aflatoxin in a food or feed product. Most recently, in 2021, a pet food manufacturer had included an ingredient that contained a high level of aflatoxin, and it unfortunately resulted in the death of at least 70 companion animals across the U.S. And more historically, in 2004, it is the largest known case of human aflatoxin poisoning that took place in Kenya in 2004 due to very high levels of aflatoxin in corn that was being sold in local villages. It resulted in over 100 deaths and a case fatality rate of almost 40%. So what are the features of an effective testing strategy for mycotoxins? Often you'll find a multi-factor monitoring strategy is most effective when you're testing inbound raw materials. Even if you're receiving certificates of analysis on inbound raw materials, the very low levels of concentration and the tendency of mycotoxins to be selective where they occur. That means that they are not widespread throughout a load or a field when they're cultivated. They can tend to be very isolated in a certain area. It's best to have a comprehensive testing strategy on inbound raw materials, in particular when you have high volumes of raw materials coming in at one time. So additional testing on top of a C of A adds additional confidence in raw material quality. Also, testing as materials come out of storage and into processing is a good way to monitor for and help prevent the introduction of contaminated raw materials in the finished product stream, and of course in secondary and co-products as well. Moving toward a more preventive monitoring model meant that testing methodologies needed to change. Typically, what the food processing customers were telling us is that we have non-technical personnel, often in the roles where we could test most easily. We also need those tests to be very fast and not technique dependent. We need them not to look like chemistry sets so that our people can feel confident running them. They can get accurate, precise results on very low concentrations of mycotoxins, and be confident enough in those results that our managers could make decisions on raw material acceptance, rejecting, or segregation based on those numbers. And we also had very frequent requests for improving safety and sustainability. There was literally nowhere to store any type of organic solvents, nowhere to safely use them in a traditional sense, no fume hoods or access to a laboratory in most cases. And therefore, these tests needed to be disposable, all-encompassing, and safe to use, as well as sustainable. When we started to understand what was needed in terms of rapid testing, we decided to come to market with first a qualitative screening tool that would allow users to receive a yes or no result at point of receival or wherever they needed it. And that was soon followed by a quantitative lateral flow approach, because we found that customers who were getting positive results on the qualitative screen really needed to know what that final number was when it exceeded the threshold. The qualitative strip tests are really attractive for their simplicity. There's no reader or investment in instrumentation required, so you can essentially be up and running in the same day with a simple kit purchase and any extraction solutions that are needed. And it's a hand-shaking extraction for 1 minute, so it can be performed by anyone. It is not technique dependent. For aflatoxin, the strip test can be used for 2 screening levels at 10 or 20 parts per billion with a small method change. And the development time for the strip is just 5 minutes, but often you'll see a test line appear within 3 minutes if it's going to appear. The qualitative strip tests were an excellent starting point for the upstream testing, but we found that customers would reach out to us when they were getting positive results and ask how they could quantify them. Sometimes there were alternative markets that raw material could be redirected to, or there was segregation possible if they had a lot of storage capacity and that product might be able to be used in another way. And it moved us in the direction of developing the Virtu quantitative lateral flow strip tests. And we launched our first strip test in 2010, and it has grown from 1 aflatoxin strip test to a whole family of 6 toxins now are possible, either singly or as a group of 2, 3, 4, 5, or 6 toxins with a single extraction. The limit of detection is as low as 2 parts per billion for aflatoxin. That's comparable to most rapid methods used in the field today. And it's also certified by the USDA Federal Grade Inspection Service. So it can be used for official export testing for aflatoxin, fumonisin, and vomitoxin. The same quantitative Virtu system can detect aflatoxin M1 in dairy products. And what makes this strip test unique is it bypasses all of the normal sample handling techniques you would expect with a milk test for aflatoxin M1, including centrifugation, filtration. Those are all completely eliminated. We're simply testing a chilled sample straight out of the refrigerator. And in one test, we're able to quantitatively detect aflatoxin M1 across the full range, covering US and EU regulatory limits. What happens on the lateral flow strip test device during testing? Let's look at an example of a sample that's contaminated with our target mycotoxin. We apply a few drops to the strip test. It begins to travel along the length of the strip and passes by a labeled antibody. It's labeled with a color indicator that the reader will recognize and be able to quantify, and it grabs the toxin and continues on the journey. If there is toxin bound to that labeled antibody, it will bypass the next step, which is the mycotoxin protein conjugate, because there's nowhere for it to bind there. It will continue to the final antibody and land on the control line, making it a more dense color on the control line and less dense indication on the test line. Once the strip test is placed in the reader is able to visualize the control line and the test line, compare them in order to quantify the final result. What if we're testing a sample that does not contain our target mycotoxin? It's also going to travel down the sorbent pad and move along the labeled antibody. Since the labeled antibody is not bound to any mycotoxin, it's free to bind to our mycotoxin protein conjugate in that first band. Any excess labeled antibody moves beyond that zone and binds to the final antibody zone, which is our control line. And so in the absence of mycotoxins, you're going to see a stronger colored test line and a weaker result on your control line. The reader will be able to visualize both of those test and control lines and use the ratio of the two to calculate a result. Whether you're running a single mycotoxin test or multiple toxins, the procedure is going to remain very similar, if not the same. We start by calibrating using a handheld barcode scanner with a barcode that is specific to that particular lot and method and commodity or commodities within that specific method. Then we weigh 5 grams of ground sample, add 25 milliliters of aqua water-based solution for extraction, vortex 2 minutes, and then filter. Once we have enough filtrate to obtain 100 microliters, we can go ahead to our next step, and we're going to apply 100 microliters of the filtered sample directly onto the strip and wait 5 minutes. Then we place it in the reader and press the center button where a digital numeric result will appear in just a few seconds. There's an optional printer that can be purchased along with the reader, and data transfer is also available to a PC. What if you want to test more than one mycotoxin at a time on a single sample? Or what if you routinely want to test 1 or 2 toxins and once in a while you'd like to do a deeper dive into your raw material stream and test up to 6 different mycotoxins? You can use the same extraction process that we looked at in our previous slide and just apply 100 microliters of that filtered extract onto each of the strips for the toxins that you're interested in quantifying. The one exception is for vomitoxin testing, you would incorporate an incubator for a brief portion of that method to make sure we have temperature stability during the analysis. Method validation for the strip test is carried out comparing the results with standard methods such as LC or LC mass spectrometry. We gear our validations to ensure that we meet the sensitivity and the range that's required not just by the industry but by governing bodies such as the USDA. And here you see we have 3 of the strip tests already approved by the USDA Federal Grain Inspection Service, and we expect more to come in the future. So when is rapid testing not just for raw material intake? When we look at this real-world example of rapid testing at the food processing facility, we can see there are multiple points where it's being used, including the inbound raw material supply. One of the co-products to flour milling is a portion of the wheat kernel that's useful for livestock feeds. And those products do not require verification because they're not going to be marketed in a consumer product, a human health product, but they do need to meet certain specifications for mycotoxins to ensure the health and well-being of the livestock animal. Those products are easily tested with a rapid method as long as they are validated and proven to be accurate and precise for that particular sample type. Look to your left and you'll see the primary finished product of the flour mill, the flour itself. Normally, you're going to see testing by a third-party laboratory for verification using LC or LC mass spectrometry, but we do see a lot of flour mills and other manufacturers who do an internal check using a rapid method, if it's available for their finished product, to do a check on their process and make sure that no mycotoxins are actually getting through from storage or from the original raw material supply. What about pasta production? You have a specialized wheat variety called durum. It's a very hard variety that is processed into semolina, and you often see testing on both of those products before processing. And finally, at the finished product, you can see a combination of internal rapid testing on the finished product because it's essentially very simple. It has the wheat, it's been processed with some water, maybe egg, and it's still simple enough to be tested with a rapid test. And they're checking their process and to make sure no mycotoxins got through the raw materials acceptance or the processing stages. And of course, the outside laboratory or internal QC laboratory verification is always a requirement for foods intended for human consumption. How about a more complex real-world example? Let's take a look at tortilla manufacturing, specifically the corn or maize version. They're going to use lime and water to cook the corn and pass it through several processing steps before it can become masa flour, tortillas, tortilla chips, or corn chips. And I apologize, we have the wrong type of tortilla in our picture here, but you get the idea. In the beginning, we're going to be using rapid tests to monitor the inbound maize. And finally, on the right-hand side, you see the dry masa flour, and that's going to be available for use in home cooking or for institutional use for further processing. Again, you see a finished product being tested using a rapid test as well as verification by a laboratory-based method. And if you look to the left, you see more highly processed finished products that are deep fried or baked, have some type of heating or extrusion applied to them, and then it becomes necessary most of the time to use a laboratory-based method to handle that complex sample matrix. Thank you for your time and attention today. If you have any further questions, please reach out and let us know in the question field of your console, and I will hand it back to Ken for a poll question. Thank you.
Thanks, Patricia. Great talk. For our first poll question, which mycotoxins are most important for your inbound raw material screening? And please choose any that apply. We'll pause for a moment while you make your selections. And thank you. For our second poll question, what is the most important feature you look for in rapid mycotoxin test methods? Please choose one, and we'll give you a moment. Now to our next speaker. Simon, please take it away.
Welcome to the second part of our webinar today on strategies for mycotoxin testing. And I want to talk about introducing selectivity and sensitivity for the determination of aflatoxins. Analytical methods are required to determine mycotoxins in agricultural commodities and food. Sampling is a critical part of mycotoxin testing. Mycotoxins are known to be unevenly distributed in foods, and so it is important to be able to detect isolated hotspots of contamination. It is therefore necessary to take many small incremental samples at various places distributed through the consignment to obtain a representative sample. This applies regardless of whether the sample is taken formally or informally, as it is impossible to confidently assess what further action should be taken based upon the analysis of an unrepresentative sample. The European Union, Codex, and the USDA all have established sampling plans for various commodities. The next stage is to prepare a sample for analysis. Samples delivered to the laboratory must be processed to generate a homogenized laboratory test sample to minimize subsampling variation. This can be achieved by dry milling or by preparing an aqueous slurry. Experimentalists identified that preparation of samples by slurrying using equipment such as a Silverstone high shear mixer offers significant advantages over dry milling. The lowest possible coefficient of variation is obtained, smaller particle sizes can be achieved, better homogenization of samples is possible, consistent results across a range of viscosities have been reported, and the materials of a wide range of sizes can be processed. Concentration of mycotoxins in samples can be very low, and the determination must be very sensitive to meet regulatory limits. Mycotoxins need to be extracted from the sample, typically using a mixture of organic and aqueous solvents. Some sort of cleanup may be required to provide sufficient selectivity and sensitivity, and we have multiple analytical challenges. Mycotoxins cover a wide range of chemical structures. They have very low regulatory limits. They are found in a very wide range of agricultural commodities, some of which are very complicated. Instrument methods are no longer just used to confirm suspect positives from screening methods, but as a primary tool for determination. Although current trends in mycotoxin analysis seem to be to go lower and lower in concentration and to try to assess more and more mycotoxins in one method, there definitely remains a need for cost-effective methods based upon liquid chromatography and optical detectors. In recent decades, methods mainly based upon high-performance liquid chromatography, HPLC, have been developed and are extensively used for the analysis of single mycotoxins or a group of mycotoxins in food and feed. Many HPLC methods have been adopted as official reference methods by the Association of Official Analytical Chemists and by the European Standardization Committee, which can be used for official control, food industry surveillance, and in cases of dispute. Aflatoxins, as shown here, are one of the most important groups of mycotoxins. Aflatoxins are present in a wide variety of crops, including corn, wheat, soy, rice, tree nuts, oilseeds, herbs, and spices. Animal products such as milk, meat, and eggs can also be at risk of contamination with metabolites aflatoxin M1 and M2. There have been a significant number of border rejections reported by the RASIF system in the European Union, especially in nut and nut products, which have led to loss of income and reputation. So let's take a look at an example of a method for determination of aflatoxins in peanuts. This is based upon a publication by the NRC Grapes Laboratory in Pune, India. The method is split into three sections: extraction, cleanup, and determination using UPLC fluorescence detection. So for extraction, in this case, we're working with a slurried sample which has been mixed with methanol, water, and salt, and then shaken for 30 minutes, and then the mixture is centrifuged. The extract is then subjected to cleanup. The main limitation of using conventional solid phase extraction is that it does not always provide sufficient selectivity. Amine affinity chromatography is a type of cleanup in which the stationary phase consists of an antibody. These columns are prepared by binding antibodies specific for a given mycotoxin to an activated solid phase support and packing the support suspended in an aqueous buffer solution into a cartridge. The mycotoxin in the extract binds to the antibody. Impurities are removed by washing the column with water or an aqueous buffer, and then the mycotoxins are dissolved with immiscible solvents such as methanol. The extract is evaporated to dryness and then reconstituted in the mobile phase prior to analysis with UPLC with fluorescence detection. The combination of cleanup using amine affinity cartridge and the determination by UPLC with fluorescence detection has been a prerequisite step to achieve the desired sensitivity and selectivity needed to check compliance with the strict aflatoxin regulatory maximum limits. The amine affinity cleanup not only removed interferences from co-extractives, but also any matrix effects. So solvent-based calibration standards can be used for quantitation rather than matrix matched. It is important to follow the procedures recommended by the manufacturers of these cartridges, even if it seems time-consuming. Special attention must be paid to the extraction solvent elution rate and column capacity to achieve optimal recoveries of targeted analytes. The use of ultra-performance liquid chromatography, UPLC, brings various benefits to this analysis. Small particle sizes in the column increases the efficiency, so it can be used to reduce the analysis time from 12 to 4.5 minutes and offers higher sensitivity than HPLC methods. The use of a quaternary system with automated blending of three solvents allows chromatographic separation to be optimized. And the use of a specialized large volume flow cell and mercury xenon lamp avoids the need for post-column derivatization. This slide shows the chromatogram with detection of aflatoxins at concentrations way below the European Union maximum level. We can also see some validation data on the right-hand side that shows the recovery and the repeatability of the method which are within the recommended limits given by the European Union. Mean affinity columns can suffer from antibody denaturation in the presence of even low concentrations of organic solvents. The extract had to be diluted to provide an aqueous solution containing little or no organic solvent. However, Vicam's new product, the Aflatest WBSR+, can endure a high concentration of organic solvent whilst maintaining excellent recoveries. The performance of this column has recently been evaluated after extraction with acetonitrile and water and was shown to be suitable for the determination of aflatoxins in a wide range of commodities. Overall recovery from a range of matrices was shown to be between 82% and 119% with a repeatability of less than 8% RSD. More details on the use of the column can be found at this link. Vicam also provide a series of multifunctional columns for the simultaneous determination of different groups of mycotoxins. The ochratoxin A is a mycotoxin produced by the same fungi as aflatoxins and co-occurs in a wide variety of agricultural commodities. The Afla-Ochra LC column produces accurate results for both ochratoxin A and the aflatoxins in a variety of commodities. This is suitable for use with HPLC fluorescence detection, but also for analysis of complicated commodities using LC-MS. Vicam also produce a mycotoxin 6-in-1 column that can be used with LC-MS for the simultaneous determination of a wider range of mycotoxins. So in summary, mean affinity chromatography is still the most powerful cleanup method for the regulated mycotoxins, especially when used before LC-based optical detection. The increase in the use of LC-MS for mycotoxin testing has reduced the reliance on these columns for cleanup, but the combination of mean affinity chromatography column cleanup and LC with fluorescence detection remains a popular option for the determination of aflatoxins. Mean affinity chromatography columns are often still used with LC-MS when low limits of detection are required and/or the commodity is a complicated matrix. And that brings us to the end of this section. I'd like to hand back to Ken.
Thank you, Simon. Fantastic insights as always. Our next poll question is, when you analyze samples for aflatoxins, do you use LC with fluorescence, LC-MS, or both? Please select one of the choices. Thank you very much. And now let's move on to our next poll question. When you analyze samples for aflatoxins, do you use official methods such as AOAC methods? Please choose one, and we'll give you a moment. Thanks. And now to our final speaker, Nicola. Take it away.
Hi everyone, my name is Nicola Derolin, and in this presentation I'm going to show a few approaches and strategies for the determination of multiple mycotoxins in confirmatory methods based on liquid chromatography and tandem mass spectrometry. The topics that I will cover are listed here. I will briefly discuss the three mostly used sample preparation methodologies, which are extraction, dilution and injection, solid phase extraction, and quenchers plus dispersive SPE. I will then illustrate why we should clean up the sample, what are the benefits of the cleanup. I will provide a few insights on what instrument we should consider for the analysis of mycotoxins, and I will finish with a quick tips and tricks session. Without further ado, let's get to it. The extraction of mycotoxins can be performed in many different ways. The cleanup can be done using a quenchers or modified quenchers with the additional dispersive SPE. It could be done by solid phase extraction, liquid-liquid microextraction, or combinations thereof. The separation and detection really depends on the sample cleanup used. For example, we have seen from the previous sessions that HPLC with fluorescence detection is usually preceded by immunoaffinity chromatography because otherwise the interferences will negatively affect quantitation. There are methods based on GC-MS, LC-UV, radioimmunoassay, electrochemical detection, and also liquid chromatography coupled to high-resolution mass spectrometry, such as QTOFs, for the screening or confirmatory purposes. But the mostly used targeted methods are based on liquid chromatography with tandem mass spectrometry, which is the core of this session. The most simple and straightforward sample preparation technique is the so-called dilute and shoot. We previously reported a method for the EU-regulated mycotoxins, which is extensively described in a document available at Waters website or scanning the QR code. In this document, we discuss why it is important to use isotopically labeled internal standards, which can be added either to the solid sample or to the final diluted extract, as described on the left-hand side. Very low limits of detections and quantitation are reached, and recoveries were between 70 and 110% for all mycotoxins. For example, for aflatoxin B1, the method LOQ was 0.1 micrograms per kilogram, and we can go as low as 0.75 picograms per milliliters in solvent standards, which means 0.00075 ppbs. We validated this method via an interlab study, where 4 different laboratories were involved worldwide. Here are 3 examples where concentrations are reported by the 4 laboratories. The red line is the assigned value of the reference material, and the black lines are the assigned value plus and minus 2 z-score. You can see how all the points stand well within the acceptable levels. The results in terms of trueness and precision were excellent. But the real advantage of tandem mass spectrometry is that we are not limited by the number of analytes in our sample, and ideally we can monitor tens and even hundreds of analytes in a single run, provided that we can reach enough separation to allow for optimal dwell time for each MS function. This is where UPLC and MSMS together find their main advantage. Here I am showing an MS method of more than 50 mycotoxins and tropane alkaloids. The sample preparation and LC conditions are exactly the same as described in the previous slides. Essentially, the method has been scaled up from the 12 regulated mycotoxins to a larger suite of emerging and masked mycotoxins. In addition to the dilute and shoot, we have the possibility to use a various range of sample cleanup techniques in order to remove some interferences and thus lowering the matrix effects. One option is the solid phase extraction, SPE. SPE can be used in so many different ways, depending on the chemical nature of the analytes and on the matrix. One way is to classify SPE protocols by using 3 main categories: trap and elute, trap, wash and elute, and pass-through SPE. Usually the sample is loaded after a proper solvation and conditioning of the cartridge. Pass-through SPE is perhaps the simplest approach as the method optimization is minimal. We recently developed and validated a method for 32 mycotoxins in various foods and feeds using the Xevo TQS Micro. In this case, we use the Oasis Prime HLB, which is a water-wettable hydrophilic lipophilic balance copolymer that does not require any solvation, any equilibration or conditioning steps. In other words, the sample can be loaded onto the cartridge straight away. 5 grams of sample are extracted with 20 milliliters of acidified acetonitrile water mix. 0.4 milliliters of supernatant are loaded onto the cartridge and discarded. Then 1.2 milliliters of supernatant are loaded and collected. Finally, the eluate is diluted 1:5 with water directly into an LC vial prior to analysis. Very simple. But an immediate question is, why are we using a 2-step pass-through SPE? Why are we discarding the first 0.4 milliliters of the sample? Here is how the two steps pass-through SPE works. Imagine that we have three analytes, A, B, and C, and one interference, D. A and B have a small retention factor K prime. They almost elute with the front of the solvent, but C is less polar, and its band is coming out later. By discarding the first fraction, we assure that we capture the three analytes where they reach the maximum concentration in the eluent. Because the cartridge behaves like a short chromatography column with about 10 theoretical plates, pass-through SPE is a rudimentary form of frontal elution chromatography. To better explain the concept of frontal elution chromatography, I put together these pictures, where we see that as the band of sample continuously flow through the sorbent, the distance between the four components are widening due to various relative retention. Compound C elutes significantly behind A and B. For this reason, collect the sample in one-step pass-through protocol is no longer desirable because the recovery of compound C will be significantly lower than A and B due to the relatively stronger retention. So we discard the beginning fraction, which contains partial B and C, and we collect the middle fraction, which contains all three compounds at full strength, whilst the interference D should be mostly retained by the sorbent. With this methodology, we get quite good method performance for all mycotoxins, including aflatoxins, fumonisins, ochratoxins, type A and B trichoticins, eniatins, citrinin, bevovericin, strigmatocystin, and also alternaria toxins. In the table, I report recovery values from a blank wheat sample spiked at concentration close to the LOQ of the method in triplicate. Additional two levels of spiking levels were tested, bracketing the maximum permitted limit for the regulated mycotoxins and up until the highest point of the calibration curve. The same experiment was performed on peanuts, figs, and animal feeds. In all cases, recoveries and RSD percentage fulfilled the criteria set by the EU legislation, and also for the emerging and masked mycotoxins, quite good results were achieved. A different but similar approach for removing some co-extractives is the modification of the quick, easy, cheap, effective, rugged, and safe, also called quenchers, and dispersive SPE. Quenchers is a simple and straightforward extraction technique involving an initial partitioning followed by an extract cleanup using dispersive solid phase extraction. Originally, the quenchers approach was developed for recovering pesticides residues from fruits and vegetables, but rapidly gained popularity in the comprehensive isolation of analytes from different matrices. I mentioned that in this case we used a modified quenchers, and by that I mean we need to use acidic conditions in order to favor the partition of the more acidic analytes such as fumonisins, citrinin, and ochratoxins into the organic phase. Here is a protocol we developed for the determination of 32 mycotoxins from different matrices. For dry matrices, such as cereals, nuts, animal feeds, etc., 2 grams of samples are mixed with 10 milliliters of water. The addition of water is important because we need to have both organic and aqueous fractions in order to induce a liquid partition. After this hydration step, 10 milliliters of 10% formic acid in acetonitrile are added, and the tube is vortexes. Quencher salts are then added and the Falcon tube is shaken. 1.2 milliliters of supernatant are transferred into the dispersive SPE, shaken and centrifuged. At this point, we have two options. We can either dilute the supernatant 1 in 10 with water and inject onto the XIVO-TQ excess with a dilution factor of 50, or we can evaporate 800 microliters of supernatant and reconstitute with 500 microliters of at least 85% aqueous and inject onto the TQS micro, resulting in a dilution factor of about 3.1. After the quenchers extraction and centrifugation, the tubes look like this, where it is clear the separation of different layers. From the top, we have the acetonitrile layer with our mycotoxins, then the solid sample, and at the bottom, the aqueous layer with the saturated buffer salts and ionic or more polar components. In this particular case, we used the same quencher salts as the CEN method 15662, and this step is effective in removing protein and starches. However, significant amounts of fats and lecithins, so phospholipids, are co-extracted along with the target analytes in the organic layer. So we take an aliquot of the supernatant and transfer into the dispersive SPE tube, which contains reverse phase sorbents such as C18 silica, plus primary, secondary amines and alumina. This quick step helps reducing the fats in alternative to traditional defatting liquid-liquid partitions with hexane or apolar solvents. PSA and alumina also provide an additional removal of sugars and other polars. This is also the reason why quenchers are usually followed by the dispersive SPE cleanup. Also, with this method, we can obtain very good quantitative results, excellent accuracy and precision. At this point, the legitimate question is, we have seen previously that we can obtain accurate and repeatable results following a simple and quick dilute and shoot approach. So, why on earth would we want to spend extra money and extra time on a cleanup post-extraction? For essentially two reasons, which are quality of the results and cost effectiveness. Here is why. I believe a photo can explain better than many words. The left-hand side photo shows a maize extract with and without applying an SPE pass-through cleanup. The photo on the right-hand side shows the same extract after evaporation and reconstitution. But also, by doing a simple experiment, we can actually quantify the amount of material we are introducing into the LC-MS system at every injection. In such experiment, I evaporated 1.2 milliliters of extract of different food matrices with and without passing the extract through the SPE. I then calculated the weight percentage difference to check effectively how much solid material is being retained by the cartridge. And we go from 16% to 66% reduction of residual weight after evaporation, meaning the SPE cleanup is really doing something here. And this is important because using the cleanup, we got from 16 to 66% fewer solid material entering the mass spec at every injection. Another good reason why we should use an SPE pass-through is because in this way we really decrease the amount of lipids in the sample. We can see here the top chromatogram of a crude wheat extract with multiple peaks of phospholipids, whilst the bottom chromatogram is the same extract after passing through SPE. Reducing the amount of unwanted co-extractives is important because we attenuate matrix effects of the coeluting analytes, but also because we reduce the rate at which charging effects occur. So what is charging effect? Charging occurs when the amount of charge being deposited onto a surface is greater than the rate at which the charge is dissipated. These are images of a TQ-XS after over 1 year of good service. And we can see how different metals components becomes contaminated by the so-called ion burns. The time scale of this effect is directly related to the ion current being injected into the MS. So it is highly advisable on high sensitive instruments to minimize the number of unwanted ions being introduced into the MS. It is important to note that this is true for all mass spectrometers for all vendors. They all become contaminated over the time, and at some point they need cleaning. System contamination can affect the data as shown in this example. This is fake data, so I made this up for example purposes. And we see a drop of peak area over the time as we keep the system running complex samples 24 hours per day, every day. The bottom plot shows the area ratio, and we can see the ratio analyzed over internal standards that is consistent over the time. So when using labeled internal standards, the quantitation is not impacted, but over a certain period of time, the response becomes too low and is not acceptable anymore, especially for low concentrations or for less sensitive analytes. When injecting sample processed by a simple dilute and shoot approach, we might find this trend. If we consider a drop to 10,000 counts as the unacceptable limit at which some intervention is needed, we can work out the time at which we need to intervene with some maintenance, such as cleaning of the cone, step wave, PM, and so on. However, when we do some cleanup, like an SP pass-through, we might experience a higher robustness of the method, which ultimately decreases the rate at which the instrument is losing the sensitivity because we are introducing less unwanted material. As a result, the system will require less maintenance and can work for longer periods of time. This means that in contract testing environments, but in every environment really, an initial investment in consumables and cleanup can actually lead to a return on investment as less maintenance can be required and we gain longer systems uptimes. This means also that we can process more samples in the same time frame, thus lowering the cost per sample of our analysis. When it comes down to choosing the right mass spectrometry system for mycotoxins, I would recommend one of these two systems. The Xevo TQ-XS on the left is the high-end, most sensitive tandem quadrupole. It can detect as low as 0.015 picograms of aflatoxins on column, which means 15 femtograms. And on the other side, the TQ-S Micro is less sensitive, cheaper, but can still reach very low concentrations. The great advantage of the TQ-XS is that we can afford to dilute the sample 40, even 50 times, while on the Micro we are limited by a factor of 20 or so. This means that on the TQ-XS we can dilute the final extract 1 in 10 with water and get good peak shapes while retaining a good sensitivity. On the other hand, on the Micro, we can dilute with water up to 5 times, but we need to find alternative ways to obtain good peak shapes for early eluters. Alternatively, an evaporation and reconstitution step is necessary. I want to finish this presentation by talking a little bit about a few tips and tricks that I found useful when analyzing mycotoxins. In particular, with respect to assuring a good peak shape, minimizing carryover, and some considerations on filtrations of the sample. The evaporation and reconstitution step is often performed prior to LC analysis, as this is a way to match the solvent composition of the diluent with that of the initial mobile phase. Also because it is an effective way to concentrate the sample. However, many times, especially in multi-residue methods, some compounds produce a loss of recovery due to two main reasons. They can be volatile or degrade with the extra heat, and they don't fully solubilize in the reconstitution solvent, mainly water. Examples are citrinine, which is volatile and almost completely lost during the evaporation, and the other examples represent compounds that are not fully solubilized into the aqueous solvent. These include eniatins, bevericin, sterigmatocystine, among others. A potential solution to overcome at least the second problem is to split the reconstitution step into two. For example, we can first add the organic portion, shake and vortex, and then we can add the water portion, shake and vortex again. Alternatively, if we have an instrument sensitive enough, we can dilute the extract instead of doing this reconstitution step. The problem is that not always we have the most sensitive instruments available, and we cannot afford to dilute the sample as much as we want because we start to lose the peak. In this case, we can still figure out a few strategies. Here I show 3 chromatograms of the same sample, an organic extract diluted 5 times with water and analyzed on a TQS micro using an FDN autosampler. The bottom chromatogram is obtained on a standard configuration. Here it is evident that there is a peak shouldering or peak splitting, which leads to bad peak shape. Therefore, we got a significant loss of sensitivity by almost 1 order of magnitude. The reason, as mentioned earlier, is a solvent mismatch between the initial mobile phase composition, which is 95% aqueous, and the sample extract composition, which is about 80% aqueous. In the figure on the right, we appreciate that at the head of the column, there is a laminar flow and a very low dwell volume, which does not allow a proper mixing of the organic layer, that is the sample, with the more aqueous layer. And this causes the partition of the analytes, represented by the red dots, into the 2 phases, pretty much like a liquid-liquid partition. This happens before the chromatography, and therefore it is spreading the analyte band before entering the column, and gives distorted peaks. 2 potential solutions when using an FDN are the inclusion of an extension loop to add more volume for an increased dispersion, like in the middle chromatogram, or to use the auto-addition functionality, where the sample is co-injected into the system with a fixed volume of water and an additional mixing occurs inside of the needle. Both options lead to much better peak shape. Another very common issue is carryover. Carryover is the result of sample left over from previous injections. This leads to ghost peak in the following blank injection. Troubleshooting carryover can be one of the most frustrating tasks for an analyst, especially if we are monitoring compounds that interact and are adsorbed on the metal surface within the flow path. Among mycotoxins, such compounds are eniatins, fumonisins, sterigmatocystine, and bevericin. A few strategies to mitigate this problem include the careful selection of the washing solution, to use metal-free needles or at least without iron, to use a partial loop mode on a fixed loop, and to change the needle seal more often. We published a white paper which provides details about this topic and uses fumonisins as a case study to locate and mitigate carryover. You can download by scanning the QR code or by visiting our website. The last tip I want to give you is, in case you didn't know already, is about filtration. Essentially, the message is avoid filtration if you can, but if you really need to filtrate because you get cloudy viscous solutions, then I would suggest using either glass fiber or PTFE membranes and avoid other types of syringe filters. With this, I want to leave you with a summary which contains the key points of this talk. Thank you everyone for your attention. Ken, over to you.
Great job, Nicola. Fine talk. Thank you very much. Our next poll question, how many mycotoxins do you run in a single LC-MS-MS method? Please choose the one that applies, and we'll give you a moment. Thank you. For our final poll question, what cleanup strategy do you use in your sample preparation method for the analysis of mycotoxins? And choose the one that best applies. We'll give you a moment. Thank you. And thank you again to all our speakers. They were great talks throughout the session, and thanks to our audience who participated in the poll questions. Now we are going to move over to our live Q&A session, but let me remind you to keep posting your questions in that Q&A widget located to the left of your screen. Any questions we can't get to, well, we'll respond directly after the event. During the transition into the live Q&A, you may hear a period of silence, so bear with us until we speak to you in a bit. Hello and welcome to our live stream question and answer portion. My name is Ken Rosnack. I have with me our three speakers, and we've also added Dan Ray and Nancy as panelists from VICAM. So welcome to all, and thank you all for staying tuned to us. Just to let you know, we've had quite a number of questions come in throughout the recordings here. We will not get to all of them, and so for those that we don't, we will be following up with an email from our speakers. So let's get right to it. Patricia, the first question comes to you, and the question is, will there be increase in the mycotoxin content when stored in optimal conditions?
Thanks, Ken. It's a very good question, and we receive it a lot, and sometimes it's hard to predict, but raw materials handlers, food processors can help to prevent any growth of mycotoxins in storage by making sure they meet certain temperature and moisture conditions when they're bringing that product in. A lot of times you'll hear the number 15% moisture. That's a very common recommendation in grain, and a temperature of about 13 degrees C or 55 F you'll want to have in those storage conditions to make sure you don't encourage further mold or mycotoxin production. But mixing, aeration, temperature, and humidity are those big factors. So yes, it can be difficult to predict.
All right, thanks, Patricia. The next question comes to Simon. And Simon, the person is asking, I'm studying mycotoxin spate during processing. Let's say that the mycotoxin is modified during processing, but I don't know what is being formed.
Okay, so we also have a question from Armando, actually, which is a similar sort of question about detecting unknown forms of mycotoxins. So I can sort of try to combine the two together. So the first approach is actually to have a really, really large panel of targeted approach. So if you look at the work of Rudy Kirschker's lab, when he's doing research into fates in storage or fates in processing of foods, he tries to cover off. He has a huge, huge LC-MS suite, which of course he has to have all the standards for. That might not be practical for most people. So the second approach is you go down a non-targeted route, and you basically acquire in a unbiased, comprehensive data-independent acquisition mode, and you're basically then relying on comparing your hits that you find in your data with some sort of library or database of known and unknown mycotoxins. So a lot of the time we know what these mycotoxins are that are conjugated or are masked mycotoxins. We just want to monitor the changes in food processing. The third approach is to carry out a sort of foodomics type approach. So you might have basically looking at a difference between a sort of contaminated and non-contaminated samples, and you can then use multivariate statistics to pull out the peaks that are actually different, either maybe during different processing steps or between contaminated and non-contaminated, and then trying to identify those. But by far the most successful approach to actually looking at this from a research perspective is to use carbon-13 labeled mycotoxins. So if they are actually added in before processing, you will be able to track where they go in terms of what metabolites they form
because they will have a unique signature from their label. And again, Rudi Koschke's lab has published on this, as well as others as well. So that's my suggestion.
All right, thanks, Simon. Very thorough. The next question goes to Nick. And Nick, the question is, which organic solvent to recommend for extracting mycotoxins in soybeans?
Thank you, Ken. So it depends. It really depends on which mycotoxin we are interested in. But for example, if we take multi-mycotoxin methods as a starting base, I will use the generally recognized 80-20 organic aqueous, where the organic is usually acetonitrile, with the addition of either acetic acid or formic acid in order to make it acidified extraction solution, in order to enhance the extraction efficiency for the acidic compounds such as fomonizins, citrinine, ochratoxin, and so on. So I will say an 80-20 organic aqueous will work also for soybeans.
All right, thank you. We'll keep the rotation going. We'll go back to Patricia. Patricia, the next question is, what is the false positive rate of these strips?
Thanks, Ken. Another very good question. And I'd like to hand that off to my colleague, Nancy Collette. She manages our tech services and applications team.
Great. Nancy?
Oh, thanks, Patricia. There's different ways of determining false positive, and some of our strips, they're yes-no strips. So typically they're evaluated at a particular level, so you can determine what false positive you get at a particular level. Usually that level is chosen below the regulatory level. So it's going to vary depending on which kit you're using. And then most of our lateral flow strips are quantitative. So we have performance data on both the yes-no test and the quantitative test, so you can get an idea of the standard deviation around certain levels to get an idea of the false positive and false negative rates. So if there's a particular test that you're thinking of in particular, one of the mycotoxin lateral flow tests, please feel free to either email us on this platform or contact us on through our website. We have the VICAM website, www.vicam.com, and just send a message out to tech service, and we'll give you the performance data on the particular mycotoxin lateral flow strip test that you're interested in.
Thanks, Nancy. Let's maybe quick go back to Nick, because it looks like there's some questions that are similar to the questions that the question he first answered. So Nick, the next question is, will FPE method work for spices? And have you checked, since it's a special matrix, will have a huge matrix effect?
Thank you, Ken. That's actually a very good question, and I'm sure that the person that asked this question has had troubles with spices, like myself. So the quick answer is no. I wouldn't recommend SPE for the cleanup of spices. What I would suggest is to use immune affinity chromatography, even if you are willing to use mass spec, so tandem mass spectrometry detection, because the extract of spices, particularly things like black pepper and so on, are very, very, very dirty. And even if applying an SPE or a quencher and disperser SPE is not enough, and the matrix effect will be huge. So I would recommend using immune affinity chromatography, like the AFLA-OCHRA or the AFLA test and so on, in order to really clean up the sample, because it's so difficult. We are about to publish a new application note where we basically developed a method for aflatoxins and ochratoxin A in black pepper using immune affinity chromatography, and that works pretty well. So yeah, again, I would recommend immune affinity chromatography for spices. For the second part of the question, we looked at different food commodities and complex samples, not just cereals. So we looked at animal feed, for example, and in that case, we were able to get good results in terms of recoveries, also for animal feed, when applying an SPE cleanup, but also a Quitchers plus a dispersive SPE cleanup.
Alrighty, thanks, Nick. Since you mentioned Nick, AfflaTest, we'll go over to Simon because there's a question to him about that. And the question is, can I use the AfflaTest WB SR Plus immunoaffinity column as part of my implementation of an AOAC method?
So this is actually a really interesting area about equivalence, about what conditions are the same as what is published in the AOC method. So if you look at the AOC methods, they generally will actually, they won't cite a specific product. They're not there to promote a specific vendor. So they will just say you must use immunoaffinity chromatography column as per the vendor's instructions. What is critical with regard to AOC methodology is the extraction. So if you change the extraction at all, then you're no longer really valid, because obviously the AOC methodology was validated into laboratory studies using specific extraction conditions. The area of uncertainty to me is at the other end. So our AOC methods for aflatoxins are not very new. They're quite old now. So they rely a lot on post-column HPLC, the post-column derivatization. And there is nothing wrong with that methodology. It is perfectly fit for purpose. But technology has moved on now, and vendors such as Waters and other vendors will offer ultra UPLC type methodology, and we have better fluorescent cells now that actually are much more sensitive. But at the moment, I don't think if you were to use the large volume fluorescent cell without post-column derivatization, I don't think you can claim that you're using an AOC method, because it's not exactly the same. We're working with some colleagues in India who have got a load of data, single lab validation, multi-lab validation that's been developed under the auspices of the AOC India section, and we wish to propose this to AOC International to be able to get this as in the first action method.
Thanks, Simon. Patricia, we'll go back to you again. And the question is, please, can you give some information about the extraction solution Aqua?
Absolutely. Thanks, Ken. Yeah, the Aqua solution, with our strip tests, it became apparent to us from the environments that our qualitative and quantitative strip tests were going into that often there was not a laboratory facility available. And what would happen when we would have a methanol or ethanol-based extraction, we would get questions around storage and safety and things like that, especially for people who hadn't been trained from a technical perspective and hadn't handled those types of things. So that was, the Aqua solution was born from that need. And it is actually a proprietary water-based buffer solution manufactured by Vicam, and we developed as closely as possible to bring a similar extraction efficiency and performance as the solvent, and I think it does a pretty good job.
All right, thanks very much. And let's see, back to Nicola. Well, here's a nice, maybe easy technical question to explain as we near the end of our time. Someone wants to know, what's an extension loop?
Yeah, thank you, Ken. So an extension loop is nothing more than a loop that you can use if you have a fixed loop autosampler, which we can also use on a flow-through needle autosampler for two reasons. The first is to increase the amount of sample that we want to inject. So, for example, if we want to inject more than 15 microliters using a needle of 15 microliters, we can use an extension loop. But the second use of the extension loop is to install this loop between the inject valve and the column in order to have more dispersion volume, and that will allow us to enable a better mixing of the injected sample with the starting LC mobile phase conditions. So it's nothing more than a loop that you could install on the inject valve and that is directly connected to the column.
All right, thanks, Nick. We have maybe time for one last quick question, and Simon, I think I'll finish with you. What are the advantages of using UPLC for aflatoxin testing over what we would term conventional HPLC?
So a UPLC system is basically it's very, very low dispersion. It can cope with high pressures that are generated by columns basically that are packed with much smaller particles. If we have much smaller particles, so we're talking generally sub-2 micron particles, we can achieve higher efficiencies. So higher efficiencies give us two options. We can get higher resolution of different components, and we can also get the same resolution, but we can speed up the chromatography. So we basically can reduce our runtimes considerably, which obviously in a busy laboratory where we are in the world, whether we're in a government or a food lab or a contract testing lab, obviously has huge consequences. The other advantage that we have is this, the not relying then on the post-column derivatization of the fluorescence to achieve sensitivity using a large flow cell on the UPLC system. So we can achieve the regulatory limits without having to do post-column derivatization. Those are the two main reasons.
Well, thanks, Simon, and thanks to all our panelists, the speakers, as well as our other experts that were on board here. And a very big thanks to all of those that attended the webinar or will soon listen to the webinar here. This is the first part of a 4-part series, so please feel free to join us in our future webinars that will occur over the next 8 or 10 weeks or so. So again, take care, everyone, and have a fine day. We will follow up with all of your questions that didn't get answered with an email from the speakers. So we do appreciate those. Keep those coming in, or also feel free to email those directly to the speakers. So thanks again, everybody, and have a good, fine rest of your day. Bye-bye.